AI has taken the world by storm. At the heart of this transformation lies a groundbreaking technology, large language models. These models are reshaping the world around us, powering advanced applications that seemed impossible in the past. Over the last couple of years, LLMs have become a subject of significant interest and at times confusion in the technology landscape. I'm Ryan Rad, and with this video, I'm excited to dive deep into some of the core concepts behind these powerful AI models, and hopefully we get ahead of some of the misconceptions that often surround them. Let's just start by defining what a language model is. Language models function as next word predictors. Consider this. When someone says, "I'm going to make a cup of," we human can easily predict that either tea or coffee will likely follow. Similarly, a language model consults a vast corpus of text and employs a probabilistic model to determine the most probable next word given the preceding sequence. In fact, LLMs assign probability to every possible sequence or order of the word belonging to a vocabulary. But language models are nothing new. They have been part of our digital lives for some time now. One familiar example is the Google search box, which suggests completions as you type. Another everyday example is the autocomplete feature on our phone's texting apps, which predicts the next word or phrase as we type. But wait, if language models are next word predictors, then how do language models actually generate an entire sentence or phrase or paragraph? Well, they do so autoregressively, predicting one word at a time based on the previous words. This predicted word then will be added to expand the existing text, and then we predict the next word based on this expanded input now. This process repeats and gradually builds up complete sentences or even paragraphs. But why are they called large language models? Well, there are two main reasons for this. First, they are trained on an enormous corpus of text, sometimes tens of trillions of text from the internet. And the second reason is that they employ sophisticated architectures with not millions, but billions of parameters. Training LLMs is a massive undertaking. In addition to the tens of terabytes of text from the internet, we will need a very large cluster of super powerful GPUs. This process is still going to take a couple of weeks, and it's going to cost a few millions of dollars. After the training is over, we are left with a file containing the model's parameters, or the trained model, which is essentially, if you think about it, a compressed version of the entire internet. And these numbers are actually true for Llama 2 70 billion parameter model. In an autoregressive way, an LLM can generate internet-like content indefinitely, non-stop, sentence after another. Now, considering that, if you want them to answer specific questions, or most importantly, you want them to stop after doing so, we need to fine-tune these models for these specific tasks. Okay, now that we have covered the basic of LLMs, let's dive a little bit deeper into how these models are developed and refined. The process of creating a functional LLM involves two crucial steps. Number one is pre-training. This is pretty much what we already talked about. And then the second step is fine-tuning. So in terms of pre-training, what we are really looking at is grabbing a big chunk of internet and then using a lot of powerful GPUs and then waiting a couple of weeks and spending a few millions of dollars to obtain a base model that can generate indefinitely internet-like content. But it won't be able to answer questions. It won't be able to do a specific task for us. And that's where fine-tuning comes in. So in case of fine-tuning, we probably going to come up with some labeling instruction. What kind of data are we actually looking for here? And then we probably going to hire people or companies to kind of collect that high quality data. By the way, this is a much less data compared to the data that we require for pre-training. So if you think about this, you can get decent result with a few hundreds of actually data, or let's say 100K would be probably more than enough for most fine-tuning tasks. And in this particular case, it could be QA. So 100,000 pairs of QA, and then we're going to use those pairs as our example input-output in order to train this model to perform QA. And this training is going to also cost much less and going to take much less time. And at the end of the day, we're going to get an assistant model. So this is a model that can actually answer question and can stop after answering those questions and understand basically the principles of QA. So there are multiple different terms for this two steps. Quite commonly, a pre-trained model is also referred to as a foundation model. So if you have ever heard of foundation models, this is basically people are talking about a pre-trained model that has not been fine-tuned. So this can be actually used as a general purpose, powerful base model for and then people can fine-tune that for a lot of different tasks. And then sometimes there's another term people use for fine-tuned model, and that is instruct model. That means instruction have been involved to fine-tune that particular model for a particular task. And obviously, obtaining a foundation model is not something we're going to do every day or every week. Only probably large corporation can do this. And even in that case, it's going to happen once or twice a year. Fine-tuning can happen a little bit more often considering the requirement and the computational resources that is involved in the process. To better understand the difference between pre-training and fine-tuning, let's use a dog analogy. Pre-training is like raising a general-purpose dog with basic obedience skills. This dog knows how to sit, stay, come when called. It has a broad understanding of human commands and can interact well in various situations. This is similar to how a base LLM has a wide-ranging understanding of language and some general information about language. Fine-tuning, on the other hand, is like training that dog for a specialized role. Imagine taking a well-behaved dog and further training it to become a police dog, learning to track, sense, and apprehend suspects, or a therapy dog, developing extra patience and gentleness for hospital visit, or a guide dog, mastering complex navigation tasks to assist visually impaired individuals. Just as this specialized dog excel in their specific roles while retaining their basic training, fine-tuned LLMs maintain their broad knowledge while becoming expert for a particular task or in a particular domains. Now that we have explored the building block of LLMs, including autoregressive modeling, distinction between foundation and instruct models, fine-tuning versus pre-training, let's see how these models can empower practical application across industries. There are generally two approaches that can be leveraged to maximize LLM's potential in context learning and model adaptation. When it comes to context learning, this includes techniques like prompt engineering and retrieval augmented generation, or RAG. These methods work within the model's existing knowledge and capabilities. So technically, we are using clever prompts or additional context to inform the model's output. On the other hand, for model adaptation, we have techniques like fine-tuning and reinforcement learning from human feedback, or RLHF. These approaches actually modify the model itself, creating a specialized version of that model for a specific task. These two general approaches differ in how they work within the token window limits and whether they alter the underlying model, but they all have something in common, and that is allowing us to get better output. We will explore each of these 4 techniques next. Before we look into the process of prompt engineering, it's extremely important to understand the key components that make up an effective prompt. A well-crafted prompt can significantly improve the quality and the relevance of the LLM output. Let's break down these essential components. We might have context. This is where we set the stage for interaction. We might have a task, which technically defines what needs to be accomplished. We might have some instruction that provides specific directions on how to complete the task. And this is the dynamic part of your prompt, or your input comes in, the specific information, question, or query to be processed. And you can optionally have formatting instruction, which specifies how the output should be structured. And again, optionally, you can even provide some examples, 1, 2, or more, that demonstrates the expected type of response. What are you hoping to get out of this LLM? Okay, here is an example that can show how these components can be incorporated into a prompt. So the context here can be, you're an expert translator specializing in idiomatic expressions. What is the task? We want to translate English idioms into French. We also want to provide literal translations and explanations. We are providing instruction that LLM should use a friendly conversational tone as explaining to a curious language learner. What's your input? The input is, it's raining cats and dogs, and the format and also 1 example is given. So this is a pretty decent and useful structure to use for prompts. Now, what is prompt engineering? Prompt engineering involves crafting and redefining prompts to get the most accurate, relevant, and useful responses from a language model. Different prompts can significantly affect the outcome, even when dealing with the exact same underlying information, difficulty of the task, or the exact same model. So, if you ever try to adjust your prompt a few times or add more context to get LLM to generate a more useful response, then you're a prompt engineer already. Effective prompt engineering is not a one-and-done process. It requires a methodological and iterative approach to achieve the best result. Let's walk through the prompt engineering lifecycle. So the first step for us is defining what do we want to achieve. What is the task here? The second step is crafting our initial prompt based on the elements that we discussed earlier. Third is time to evaluate this prompt design that we came up with. And the next step is our opportunity to revise our prompt based on the evaluation results. And now, this step can iterate as many times as it needs to be, and it's called prompt tuning, where we keep revising the prompt and evaluating until we are satisfied with the outcome. And then we deploy that prompt design into a real-world application. But as we use this prompt in a real-world scenario, we will keep gathering new data and insight every second, every minute, which allows us to continually refine and improve our prompt design over time. But that was just the framework of prompt engineering. Let's look at some of the prompt engineering techniques that we use in real world. The first technique I have here is few-shot learning. This technique provides examples to guide the model responses, helping it understand the desired output format and style. Another technique is called task decomposition. For complex queries, breaking them down into smaller, manageable subtasks can often lead to more accurate results, especially because solving each of those subtasks is a lot easier than solving the whole problem for LLM. The other technique is chain of thought. This approach encourages the model to break down complex problems into steps, often leading to a more logical and explainable output. We can think of chain of thought as a special case of task decomposition. The other example I have here is self-consistency. This is one of my favorites. By generating multiple responses and selecting the most consistent one, this technique can improve reliability. And finally, RAG, or Retrieval Augmented Generation. This powerful method incorporates external knowledge and to enhance the response, which we will explore in more depth shortly. Prompt engineering is easy to implement and sometimes can actually yield amazing results. However, they are just not enough in a lot of different scenarios. And in order to understand why, we just need to really pay attention to the fact that LLMs generate text based on probability, not stored facts. Let's see an example where prompt engineering won't be able to help us. So here is the question. Can I recycle pizza boxes in Boise, Idaho? So a typical LLM answer would be, unfortunately not. Generally, pizza boxes are not recyclable due to food contamination. However, if we actually look at some official resources from city of Boise and local news articles and so on and so forth, and if we augment the prompt with this external information, then LLMs would be able to tell you, oh, unlike many other cities, you're in luck. Unlike many other cities, Boise, Idaho actually does accept pizza boxes. So if we need the model to use very specific information, then we need to provide it in the prompt. LLMs are quite sensitive to the content of their prompts, and they usually stay grounded and true to that in their answers. As you can see here, RAG allows LLMs to access and incorporate up-to-date, location-specific information, leading to a more accurate and helpful response. All right, now that we have seen the power of RAG, let's take a closer look at how it works. The RAG framework combines the strengths of LLMs and their underlying understanding of the language with external knowledge retrieval. First thing first, we will need to gather useful external information that will help us perform the task that we are expecting. Then we're going to split external data into chunks. There are multiple different ways how to do that. We're not going to get into that in this video. And then we're going to embed these chunks into vectors, and then we're going to store these vectors into a vector data set. Now, when a query comes in, we're going to embed it and store it in a data set. And then we're going to look into vector similarity to kind of fetch the most relevant splits from the external knowledge to augment that with the existing prompt. And that's going to give us enriched prompt or augmented prompt. And hopefully this prompt contains everything an LLM might need in order to generate a more informed, detailed, and accurate answer. While in-context learning techniques like prompt engineering and RAG are very powerful, most importantly, faster and easy to implement, and they can apply on the fly during inference time without any additional training step, they have their own limitation, and these methods operate within the confines of models' existing knowledge and token window, which can be restricting for complex and highly specialized tasks. We often encounter scenarios in real world where simply providing context or a clever design for the prompt is not going to be enough. This is where model adaptation techniques comes into the play. Fine-tuning LLMs involves training the model on pairs of prompts and compilations tailored to a specific task or domain. This process allows us to specialize a general-purpose LLM or a fine-tuned LLM to another particular application. This can be customer service, medical diagnosis, legal document analysis, translation, and so on and so forth. By exposing the model to many examples of the desired input-output pairs, we can guide it to produce more accurate and relevant response for our specific use case. Our final topic brings us to one of the most recent development in LLM technology, reinforcement learning from human feedback, or RLHF in short. RLHF is based on a simple yet powerful idea. It's just way easier to recognize a good answer rather than to generate one from scratch. This approach uses human feedback to further refine model output, leading to a more natural, helpful, and aligned responses. So the way this is going to work is we can apply this in a semi-automated way. We can ask LLM to generate, or multiple different LLMs to generate different answers, and then we can, as a human, we can rank those answers. So let's see one example here. I asked an LLM, write a haiku about machine learning. And then I got 3 different answers. And it's just way easier for me to say which one I like the most and which one is the best and second best, and then my actually least preferred answer. Okay, now that we have explored these 4 powerful techniques for leveraging LLMs, let's put them into perspective. To better understand when and how to apply each method or a combination of more than one method, we can visualize them along 2 critical dimensions: the degree of model adaptation required and the extent of external knowledge used. So first, we're going to look into where prompt engineering falls in this space. Prompt engineering would be a great use case for a daily general purpose task scenario. Let's say a company wants to use LLM to generate product descriptions for their social media or e-commerce website. They can craft and design a specific prompt to guide the model in creating consistent brand align without the need to modify the model or requiring extensive external data. Let's see where RAG falls in here. If you need a question answering system, which typically would require up-to-date information, let's go with a legal firm example that needs an AI assistant to answer questions about current laws and regulations. RAG allows the LLM to access and incorporate the latest legal information from external data sets without modifying the base model. Let's see where fine-tuning falls in this space. If we have a specialized domain application, such as a healthcare provider who wants to create AI system for medical diagnosis, well, they can fine-tune, and they should, and they need to do so, using a data set of medical records and symptom diagnosis pairs, creating a specialized model for their specific use case. And finally, RLHF falls here. Let's say if you want to develop AI assistant with aligned behavior, one example would be, let's say a tech company is creating a general purpose AI assistant. Well, they can use RLHF to refine the model's responses based on human feedback, ensuring the assistant provides helpful, safe, and ethically aligned output across a wide range of typical topics and situations. All right, that's all for today. Thank you for watching, and I will see you in the next video.